So today's lecture is on design of rigid pavements. So rigid pavements, they do not flex much under loading like flexible pavements. They are constructed using cement concrete. In this case, the load carrying capacity is due to the rigidity and high modulus of elasticity of the slab. So H.M. Westergaard is considered one of the pioneer in providing the rational treatment of the rigid pavement analysis. So coming to the general design considerations, so the cement concrete pavements, they represent the group of these rigid pavements. So the Westergaard, he considered the rigid pavement slab as a thin elastic plate which is resting on the soil subgrade, which is assumed as a dense liquid. Okay, here it is assumed that the upward reaction is proportional to the deflection, that is P equals to K delta, where K is the modulus of subgrade reaction. Okay, and its unit is kg per centimeter square per centimeter deflection, that is kg per centimeter cube. Okay, so Westergaard's modulus of subgrade reaction. So the modulus of subgrade reaction, that is capital K, it is proportional to the displacement. So if P is the pressure which is sustained in kg per centimeter square by the rigid plate of diameter 75 centimeters at a deflection delta which is given to as 0.125 centimeters, then the modulus of the subgrade reaction K, we can find it by using in this equation here. K is P upon delta, where delta is taken as 0.125. okay, so coming to the next is the relative stiffness of the slab to the subgrade. So a certain degree of resistance to slab deflection is offered by the subgrade. Now the tendency of the slab to deflect is dependent upon its properties of the flexural strength. Okay, the resultant deflection of the slab, which is also the deformation of the subgrade, is a direct measure of the magnitude of the subgrade pressure. So Westergaard, he defined relative radius or relative stiffness, and he gave an equation to it, which is L. Okay, L equals to EH cube upon 12K 1 minus nu square okay raised to 1 by 4, where L is the radius of relative stiffness. Okay, which is given in centimeters. Then E is the modulus of elasticity of the cement concrete, which is given in kg per centimeter square. So modulus of elasticity of cement concrete okay kg per centimeter square. Next, nu is the Poisson's ratio for concrete, which is taken as 0.15. So nu is the Poisson's ratio. Just take 1 equals to 0.15. H is a slab thickness. It is given in centimeters. Okay, and K is the subgrade modulus or the modulus of the subgrade reaction, which is given, its unit is kg per centimeter cube. So K is the subgrade modulus or modulus of subgrade reaction. Okay, kg per centimeter cube. Okay, so radius of relative stiffness is given by this equation here, EH cube upon 12K 1 minus nu square raised to 1 by 4. So let us take down a problem here. Let us see this problem. So let us read this. Compute the radius of the relative stiffness of 15 centimeter thick cement concrete slab from the following data. Okay, modulus of elasticity of the cement concrete is given to us as follows, and Poisson's ratio is also given to us, and modulus of subgrade reaction is also given to us. So we need to compute the radius of the relative stiffness. So let us see how it is calculated. So we know the formula for radius of relative stiffness as L equals to EH cube upon 12K 1 minus nu square raised to 1 by 4. From the previous slide, we have already seen the formula for radius of relative stiffness. So let us see solution to this. So K value is given to us. So let us see radius of relative stiffness L equals to, substitute this in this equation here. So EH formula is EH cube, okay, upon 12K 1 minus nu square, okay, raised to 1 upon 4. Substitute this in this equation, all these values which are given here. So this will be 2 1 0 0 0 0 into H value is given to us as 15. So into 15 cube upon 12 into 3, okay, 1 minus 0.15, okay, square, the whole raised to 1 by 4. So this value comes out to be as, after solving this, you'll get it as 67 you'll get it as 67 centimeters. Okay, next, coming to the critical load positions. So since the pavement slab has a finite length and width, either the character or the intensity of maximum stress which is induced by the application of a given traffic load is dependent on the location of the load of the pavement surface. So you can see here there are three typical locations, namely the interior, edge and the corner. Okay, interior, edge and the corner. So in the interior loading, when the load is applied on the edge of the slab surface at any places removed from all the edges. So in the edge loading, what happens is when the load is applied on the edge of the slab at any place removed from a corner, and in corner loading, when the center of the load application is located on the bisector of the corner angle, okay, formed by two intersecting edges of the slab, and the loaded area is at the corner touching the two corner edges. Okay, so these are the termed as the critical load positions. Coming to the next is the equivalent radius of the resisting length. Okay, so considering the case of the rigid case of a interior loading, the maximum bending moment occurs at the loaded area and acts radially in all directions. So according to this Westergaard, the equivalent radius of the resisting section, okay, in terms of radius of the load distribution and the slab thickness, he gave a formula for this. So let us see the formula according to Westergaard. Okay, the equivalent radius of resisting section is given as B equals to square root of 1.6 a square plus 8 square minus 0.675 h. Okay, where B is the equivalent radius of resisting section in centimeters. Okay, A is the radius of the wheel load distribution, H is the slab thickness. Okay, so you know B is the equivalent radius of resisting section okay, then A is the radius of the wheel load distribution, radius of wheel load distribution, okay, in centimeters, and H is a slab thickness. Okay, so this is the formula to calculate the equivalent radius of resisting section according to this Westergaard. So let us see this problem here. So compute the equivalent radius of resisting section of 20 centimeter slab, okay, given that the radius of the contact area wheel load is 15 centimeters. So we need to calculate the equivalent radius, that is we need to calculate B. So what is given to us? A section of 20 centimeter slab thickness. So H value is given, the slab thickness, and the radius of the contact area wheel load is 15. So A is given to us. A is the radius of the wheel load distribution. So let us see here. So what is given to us? H is given, that is slab thickness is given to us. H equals to 20 centimeters. This is given to us in the problem. Next is given to us is the radius of the contact area wheel load is 15 centimeters. So A is the radius of the wheel load, which is given to us as 15. Okay, so A upon H is 15 upon 20, which is 0.75. Okay, so this is less than 1.724. So if A is greater than 1.724 H, okay, the value of B will be equal to A. Okay, if A is greater than 1.724 H, value of B will be equal to A. So here it is less than 1.724. So B will be, need to calculate, B equals to square root of 1.6 A square plus H square, okay, minus 0.675 H. Okay, so substitute these values in this equation here, which is 1.6. what is the A value? A value is 15, so 15 square plus H value we know it as 20, so 20 square minus 0.675, H is 20, so into 20. Okay, so this value works out to be 14.0. okay, 14.0 14.07, okay, 14.07 centimeters. Okay, B value we got it as 14.07 centimeters. That's the answer here. Okay, next coming to the wheel load stresses. So A.T. Goldbach, okay, he indicated that many concrete slab failed at the corners. Okay, so he derived a corner load formula due to a point load at the corner of the slab. Okay, so Goldbach's formula for stress due to the corner load is given by SC. Okay, where SC is the stress due to the corner load. So he gave the formula as SC. SC equals to 3P upon H square. Okay, where SC is the stress due to corner load. Stress due to corner load in kg per centimeter square. P is the corner load. Okay, assumed as a concentrated point load which is in kg, and H is the thickness of the slab. Okay, this is given in centimeter. Okay, so this is the formula to calculate the stress due to corner load, which is given as SC equals to 3P upon H square, where C is the stress due to the corner load. Okay, P is the corner load and H is the thickness of the slab, which is given in centimeter. Now Westergaard's stress equation for the wheel load. Now the cement concrete slab is assumed to be a homogeneous thin elastic plate, okay, with subgrade reaction being vertical and proportional to the deflection. So here Westergaard he considered three typical regions of the cement concrete pavement slab for the analysis of the stresses. So these regions are as interior, edge and the corner regions. So some formulas he has given to us, like for interior region, okay, the critical stresses where SI, SE and the SC are the maximum stress at the interior, okay, edge and the corner. So for interior loading, SI is given as 0.316 P upon H square 4 log 10 L upon B plus 1.069, where H is the slab thickness, okay, P is the wheel load, A is the radius of the wheel load distribution, L is the radius of the relative stiffness, okay, and B is the radius of the resisting length. So for edge loading, it is SE, which is 0.572 P upon H square 4 log 10 L upon B plus 1.359, and for corner loading, SC is 3P upon H square 1 minus A root 2 upon L. Okay, so these are the formulas to calculate the interior loading, edge loading and corner loading. Okay. So evaluation, next is evaluation of the wheel load stresses for the design. So Westergaard's wheel load stress equation for interior, edge and the corner have been modified by various investigators, okay, based on their research work on cement concrete pavement slabs. So the stresses at the edge and the corner regions are generally found to be more critical for the design of the rigid pavement for highways. So the Indian Road Congress recommends the following two formulas for the analysis of the load stresses at the edge and the corner regions and for the design of the rigid pavement. So Westergaard's edge load formula, which is modified by Taylor and Sutherland for finding the load stress SC in the critical edge region. Okay, he is given by this equation here, which is SE equals to 0.529 P upon H square 1 plus 0.54 nu into 4 log 10 L upon B plus log 10 B minus 0.4048. So this equation, okay, is used is by Westergaard's age load formula, okay, which is modified by Taylor and Sutherland. This is used for finding the load stress SC in the critical age region. So next, Westergaard's corner load stress analysis, again modified by Cayley, for finding the load stress SC in the critical age region. So this is given by this formula SC, that is critical age region, which equals to 3p upon h square 1 minus a root 2 upon L 1.2 raised to 1.2. Okay. So where SC is the load stress at the age region, which is kg per centimeter square. SC is a load stress of the corner region, okay, and SE is the load stress of the age region. P is the design will load. H is the thickness of the cement concrete slab. Nu is the Poisson's ratio, okay, of the cement concrete slab. Capital E is the modulus of elasticity of the cement concrete slab in kg per centimeter square. Okay, now K is the reaction of the modulus of the pavement foundations, okay, that is for base course, sub-base course, and L is the radius of the relative stiffness. So B is the radius of the equivalent distribution of pressure. So B equals to A when A upon H is greater than 1.724. If it is A by H is less than 1.724, B will be equal to root of 1.6 A square plus H square. Okay, so in this case, if B equals to A when A upon H is greater than 1.724. Okay, now if A upon H is less than 1.724, B will be square root of 1.6 A square, okay, plus H square, okay, minus 0.675 B. Okay, so this condition arises when A upon H is less than or equals to 1.724. Okay, so A is the radius of the load contact area. So these are the age load stresses here. So these charts are applicable for a particular set of design parameters. Okay, so P equals to 5100 kg is given to us. Okay, in this chart E values are given, nu is given. So it's a stress to find the age load stress, okay, slab thickness and the age load stresses. So we can find the age load stresses with the help of this chart here, okay, corresponding to this K values, okay, and the slab thickness. Similarly, for corner load stress, we can find the corner load stress using the K values here, and the slab thickness correspondingly we can find the corner load stresses. Coming to a problem, so let us read this. So what is told to us: calculate the stresses at the interior, edge and the corner regions of a cement concrete pavement using the Westergaard stress equation. So use the following data. So what is given to us is the wheel load is given to us as 5100 kg. Then the modulus of the elasticity of the cement concrete is given to us as 3 into 10 raised to 5 kg per centimeter square. Pavement thickness is given as 18 centimeters. The Poisson's ratio of concrete, okay, nu is equals to 0.15 is given to us. Modulus of the subgrade reaction, that is K, equals to 6 kg per centimeter cube, and radius of the contact area is given to us as 15. So we need to calculate the stresses at the interior, edge and the corner regions using this data. So let us see how it is done. Coming to the solution of it. So first of all, in order to calculate, okay, the stresses at the interior, edge and the corner, we need to first calculate the radius of the relative stiffness, okay, because we need them in the formula to calculate the stresses at the interior, edge and the corner. So let us calculate the radius of the relative stiffness, so which is given to us as small l. So radius of relative stiffness, okay, L, it is given as small l. So L equals to E H cube upon 12k 1 minus nu square, okay, raised to 1 by 4. Substitute these values are given to us E, H, K, nu. It is given to us in the problem. So substituting all these values in this equation, okay, E is given to us as okay 3, it is given. H value is given to us as 18, okay, K value we know as 6, new value is given to us as 0.15. So let us substitute it in this equation here. Which is 3 into 10 raised to 5 into H is 18 cube upon 12 into 6, K is 6, okay, 1 minus nu is given to us as 0.15 square, okay, raised to 1 by 4. So this value works out to be 70.6, okay, 70.6 centimeters. Next, let us find the equivalent radius, equivalent of the resisting section, okay, which is given to us as A upon H. So the equivalent of resisting section, okay, which is A upon H equals to 15 upon 8, okay, which is 0.833 less than 1.74. So this is less than 1.74, so this condition will be B equals to square root of 1.6 A square plus H square minus 0.675 H. Okay, so substituting all these values here, .6 A is 15 square, okay, plus 18 square minus 0.675 H is 18, so 18, okay, so this will be equal to, this works out to be 14 centimeters here, so 14 centimeters. So now let us calculate the stresses at the interior edge and the corner. So we already know what is L, what is B. Okay, so let us proceed further to calculate the stresses at the interior edge and the corner. So stress at the interior, that is SI, stress at the interior SI, okay, this is given by this formula. We know that SI equals to 0.316 P upon H square, okay, 4 log 10 L upon B, okay, plus 1 0.069. Okay, so this is the formula to calculate the stress at the interior. So we know all these values here. LB we know what is B, we know what is H. So substituting all these values in this equation here, okay, so this will be 0.316, okay, into we know P as 15100 upon 18 square 4 log 10 70.06 was L value. So 70.6 was the L value, and B was 14. Okay, B was 14. So 14, substituting this equation here, so plus 1.069. Okay, so this value works out to be 19.3. okay, get it as 19.3 kg per centimeter square. Okay, so this is the stress at the interior, that is SI. Next, let us see stress at the edge and the stress at the corner. So stress at the edge, that is SE. Okay, it is given as SE. So SE will be equals to 0.572 P upon H square 4 log 10 L upon B plus 0.359. okay, substituting all these values, we know L, we know B, we know P, we know H. So let us substitute this in this equation here. So we know all these values, so 0.572 into 5100 upon 18 square, okay, 4 log 10. Okay, what is L value? We know L value is 70.6. okay, B value also we know as 14 plus 0.359. okay, so this value works out to be 28.54 kg per centimeter square. Okay, then next is stress at the corner. So stress at the corner, that is SC. okay, SC. So SC is 3P upon H square 2 minus A square root of 2 upon L 0.6. okay, so again substitute all these values here. A is 15, okay, L is 70.6, P you know as 5100, H is 18. So after that you will get this, some simplifying all this, you will get it as 24.27, okay, kg per centimeter square. So we have calculated the stresses at the interior, at the edge and the corner. So let us see the next problem. So a cement concrete pavement of thickness 20 centimeters resting over a WBM base course with modulus of the reaction is given to us as 30 kg per centimeter cube. We need to find the load stress. Okay, we need to find the load stress at edge and corner regions under a wheel load of 5100 kg unit IRC stress chart. Okay, so we need to assume this A as 15, E equals to 3 into 10 raised to 5 kg per centimeter cube, and U is 0.15. So we need to find the stresses at the edge and the corner regions using the charts. Okay, let us see how to find this. So this is a edge load stress chart. So with the help of this chart we can find the edge load stresses. So in the problem we already know what K value is known to us. Okay, so let us see how to find it. So we need to refer the edge load stress chart as I told you. So using the curve K equals to 30 kg per centimeter cube and corresponding to H equals to 20 centimeter. Okay, this 20 centimeters is already given to us in the problem. So H is 20 centimeters, SE will be 22. So K is 30, this curve here, K is 30, and the slab thickness H is already given to us as 20. So H is 20 here. Okay, so corresponding we know this H is 20, this curve K value is given to us in the problem as 30. So what will be the edge load stress? Okay, it will be around 22. So corresponding to this we have to find it out. What is the edge load stress? So we are getting it as 22. Is it clear? So this curve is 30 K value and corresponding we know H value as 20. So 20. So edge load stress will be 22. Around here it will come, edge load stress. So this is the way SE we can find it out. So SE will be 22. Similarly, referring to the corner load stress chart, we know K value is given to us and H is given to us as 20. Okay, so similarly for corner load stress chart, okay, similarly for corner load stress chart, we know K is 30. Okay, this curve you have to refer since it is given to us in the problem as K equals to 30. So K is 30. Okay, and this is given to us, H value is given to us, right? H is given to us as 20. So this correspondingly to this curve and this value for slab thickness here, we are getting it as 25. Clear? This is 25. 20, and this curve here, which is K is 30 centimeters. K is 30 kg per centimeter cube. So 20 and this curve here, so we'll get it as SC. Okay, that is the corner load stress. We'll get it as 25. Okay, so with this the problem is ended. Okay, so with this I end my lecture.